My name is Katia Moskvitch, and I'm the editorial lead of IBM Research. And we are here today at IBM Research Europe in Zurich, Switzerland. Next to me here is a full-size model of a quantum computer. So I know it looks like a really pretty chandelier. I realize that, but actually it's not, even though I would love to have one in my house. I think it looks super cool, but it is a model of a quantum computer. And that's what we're going to be talking about today, the state of quantum computing. Joining me today is one of my amazing colleagues, IBM physicist Heike Riel. She's going to be joining us from Quantum Lab here at IBM Research Europe. And she is actually the quantum lead of IBM Research Europe. Fun fact, by the way, before switching to physics, Heike used to design furniture. I think it's actually quite amazing as far as career switches go, from furniture design to quantum computing. Heike is also an IBM Fellow, and as of late last year, she actually became a Fellow of the American Physical Society, which is a pretty huge honor in physics. So before I hand it over to you, Heike, I actually wanted to say welcome to everybody who's watching us. Please do send us your questions on YouTube. We'll try to get through as many questions as we possibly can during the discussion. And with that, Heike, over to you. Tell us where you are. Tell us what is that big, weird white cylinder next to you.
Yeah, hi, Katia. Great seeing you here, although you are in a different building, right? So we are here live in one of our quantum labs at the IBM Research campus in Zurich. And you've seen the pretty picture of the Zurich campus on top at the beginning. It's really a beautiful campus, but it's not only a beautiful campus, but also a beautiful and very exciting lab here. Because we are actually next to a lab where 35 years ago, Nobel Prize winning experiments were done. And my colleagues at that time, they discovered high temperature superconductivity. So back to your question, Katia, of where are we, what are we seeing here? And so behind me or next to me, you see actually one part of a quantum computer, right? It's a more complex thing. What you see here is a dilution refrigerator. We call it also fridge, and it actually cools down the quantum processors to very low temperature and much lower than actually your fridge at home where you store your food. So it goes down to almost zero temperature, to about 10 to 20 millikelvin. This is how cold the quantum processor needs to be. And you see it's also quite a big thing, as you've seen. And we also have connected to the fridge here, then also electronics, where we then can communicate with the quantum processor.
So hold on, Heike, that's really cold. But is that, I heard, correct me if I'm wrong, but I heard that it's like the coldest place in the universe. Is that right? Like it's colder than outer space or something like that? Is that true?
That's definitely right. It's actually about 100 times colder than outer space. And I mean, this is a demonstration also of what technology is able to do, right? It cools down things. And actually today it's done in a quite engineered manner. Like 20 years ago, this was much more cumbersome for physicists to do these low temperature experiments. But today, that's really a technology which is very much used and not so much of a difficulty anymore.
Wow, well, that's indeed amazing. Well, can we actually see the inside of that fridge, or would we be able to, open it up and see the model that we see here?
Yeah, so unfortunately in the lab here right now, we cannot uncover this thing because we're actually doing experiments. So my colleagues, they actually run experiments right now. Therefore, the fridge has to stay complete and cold. But what you see here now in the video, which is shown, is how this fridge is kind of uncovered to the inside. There are different cylinders which need to be taken off when you need to exchange the quantum processor. And then you see the inner core of the inner life of the quantum computer. And perhaps we can also show a more detailed picture of the inner life, as we can't see it very well. And I explain a few things towards that. So because we have the electronics outside, we have room temperature outside, but then we go to a temperature 100 times colder than outer space. And so we run actually here, what you see in this figure is actually that the quantum processor sits behind this cylinder at the bottom, which you see. And this is where the coldest spot is in the quantum processor. And then what you also see are these lines which are running down. And these are superconducting coaxial cables where actually microwaves are transported in order to talk to the quantum processor behind. And all this is inside this fridge. It's currently used, and that's why we can't open it, Katia.
But wow, well, that certainly looks very futuristic, right? And even much cooler than this model next to me. I now feel like I would love to be next to the real thing. But also, I remember the first time I visited IBM Research a couple of years ago, and I remember entering the quantum computing lab and like looking around, like thinking, okay, where is the keyboard? Where is the screen? Like, where is the quantum screen? I was thinking, So definitely it doesn't look like a regular computer, right? It looks like, as I said, the chandelier, but not a regular computer at all. And you mentioned microwave pulses, Heike. Is that like the same kind of microwave radiation that I use at home when I don't know, warm up my pizza in the microwave? Also, you probably shouldn't do it with pizza, but is that the same thing?
Yeah, it's also microwaves. It's a bit of a different frequency which we are using, but we use these microwave pulses to actually talk to the quantum processor, to bring information in, to run the calculation, and then also read out the result of the calculation. And as you said, it's not like a typical classical digital computer, as you know, where you have a keyboard and you have a screen and it's used transistors as the smallest parts of it, but it's a completely different mechanism and physics behind how these computers work. So actually in these quantum computers, there are qubits used, so-called quantum bits, which are actually the unit of information carrier here. And in classical digital computers, which we all know, we use so-called bits. And we know that they can be a 1 or a 0, and then we can encode information in these 1s and 0s, and we can do processing of information. So in the quantum computer, it's really working different because the laws of quantum physics are used to do calculations. And so, as I mentioned, we use quantum bits or qubits, and they can be a 1, a 0, or something in between. So this is one quantum phenomena. There are actually other quantum phenomena also used for the calculations, like entanglement and interference. And because of this quantum mechanics and quantum physics, the power of these quantum computers can be really exponentially different than the classical computers. And that makes them really interesting and really a breakthrough technology which is coming.
That sounds really cool, but can we already use them today? Like, can I access one and use it freely for like whatever I'm working on?
Yes, actually you can, and you can do this already since 4 years, because already in 2016 we have brought the first quantum computer at that time with 5 qubits to the world. We made it accessible through the IBM cloud. And people could just, log in using a normal classical computer to log into the quantum computer and run quantum algorithms on the computer. Of course, a lot has changed, right? And for me, it's actually very exciting because when I studied physics, it was kind of a theoretical concept which was discussed, but now they're real. And in the last 4 years, so many things have happened. Great technological development and breakthroughs have been accomplished. We have increased the number of qubits from 5 to 65. Also, the quality of the quantum computation was increased, though this is measured in quantum volume. I don't want to go into detail in that, but a lot of things have really happened. So it's not only something which just stands in the lab like here where we do experiments, but it's actually already moving into data centers where they are used through the cloud as normal devices.
Wow, okay. Well, it does sound very impressive. I don't know about the rest of the audience, but I am, positively impressed. So, how can I use them? You said I could use them. So can I use a quantum computer to, I don't know, create like a better PowerPoint presentation or something? Although that's by PowerPoint. PowerPoint probably is not the best example, but, why don't you tell us what we can use it for?
Yeah, so it's probably not the best use, to be honest, right? For text processing or doing better presentations, it's really not the right means, because you have to solve problems with a quantum processor where the nature of quantum physics can really help you. And but these challenges or these problems are actually there in many industries. So these are mathematical problems where the complexity of the calculation actually increases exponentially with the number of parameters, for example. And this can be in materials analysis or materials development. If you're looking for new molecules, and these molecules can actually not precisely calculated by digital classical computers, because molecules are also based on the quantum mechanics. And so building computers which intrinsically exploit quantum mechanics is a much better tool to calculate the properties of molecules precisely, and thus be able to also predict new molecules or new materials. Why is this important? Materials you can find actually in almost every industry. Whether you go into the car industry, you need better batteries, you need better materials for batteries. You want to have more lightweight materials. If you look into energy, you want to also have like materials which can absorb carbon dioxide. So there are a lot of these materials challenges where innovation in materials can bring a big value. Also in transport, supply chain, right? If you have difficult routes, if you have manufacturing processes which need optimization, also for finances industry, there are many different examples where these mathematical problems appear, which today in classical computers we only use like approximations, but they cannot always solve your problem.
Mm-hmm. Wow, okay. I can see that questions are actually starting to come in, Heike. So there is a question for you here. I'm just going to read it. Doesn't the temperature create problems, like some kind of shrinking of the materials due to the low temperatures?
Yes, it's right that materials shrink when you cool things down. And you have to take these type of things into account, right? When you build, for example, devices, then the materials should have like similar temperature behavior. Otherwise, you can run into problems. But there is actually a lot of knowledge in research in doing those temperature characterization and experiments. And so we have learned also how to build those devices that they kind of work and survive these low temperature, that you can heat them up again and that you can cool them down again and they still work.
Wow, that definitely sounds fascinating. So just to back up a bit, so you were talking about these different applications for quantum computers. And I think you mentioned like chemistry and finance. So if I understand correctly, it has to do with optimizations. So maybe I could even input my picture in a quantum computer. It would give me lots of different options of how to, style my hair or like get a new haircut. Or do you think we're going to be using quantum computers for stuff like that? Or it's never going to be used by individuals, but mostly like to solve global problems?
So I'm not so sure about your haircut, whether it helps you there, right? But as mentioned, there are really very exciting or very important problems, technical problems in many different industries, which can benefit of quantum computers. And there are different classes. One is for sure the optimization of, as I mentioned, like transport routes, or in the finance industries, if you want to do risk analysis, you have to do Monte Carlo simulations, for example, and also in quantum Monte Carlo simulations can help you. So we actually have here developed in IBM a quantum algorithm which can be used. And this, we also demonstrated that this can create a significant advantage and can speed up the things quadratically.
Mm-hmm. Great. I have another question that just came in for you, Heike, and it has to do with quantum superposition. Could you please explain to us very simply what quantum superposition is?
Yes, so that's a phenomenon. You know, having graphs, it's much easier to explain. But let's start like this. And you have like a imagine an arrow which can point up or can point down, and so to the North Pole or the South Pole. And this gives you like a 1 or a 0 state, right, represented. And in quantum computing, you can actually create a superposition out of these two vectors. This means you can take a number of times the up arrow plus a number of times the down arrow. And this is a new state, which can also be represented by the quantum bit. And in the end, you can visualize this by the so-called Bloch sphere, where every state on the surface of a sphere can be represented by this superposition. And so you can imagine now with these 1 qubit, you can describe every position on the surface of the Bloch sphere. And this is one mechanism of why quantum computers are so powerful.
Mm-hmm. Wow. So just to clarify, though, so when you're describing qubits, they clearly behave like atoms, but they are something physical, right? That we actually create, like what's inside a quantum computer. Like, can you just describe a little bit what a qubit would look like, I guess, to human?
Yes, a qubit can also be called kind of an artificial atom. And why is it called like this? In an atom, you have like, and it goes a bit deep into physics, I'm sorry about that, but you have different energy levels in an atom, and you in principle create now an artificial atom which also has different energy levels. And these, you need two, because these two represent kind of your 1 and your 0. And you can implement them in different physical systems. What we use here in our quantum computers are superconducting Josephson junctions. And these are actually, it's kind of a, we can call it a simple structure, because in the end it's 2 superconducting metal layers which have an insulator in between. And there you can create kind of these quantum states, which you can then use for your quantum calculations.
Mm-hmm. Okay, great. Wow. And where are we today with quantum computers then?
Yeah, today it's really exciting. As I mentioned, we have increased the number of qubits. We increased the quality of the measurements and the control of the qubits. We have also, designed and engineered the system to be more robust and stable, to kind of improve really all the different parameters. And just at the end of last year, in September, we have also announced the roadmap which we are pursuing. In this roadmap, you actually see the different processors, the different quantum processors. And last year, we have demonstrated the so-called Hummingbird. It has 65 qubits. And we are now on a path to really increase the number of qubits continuously. So this year, we will demonstrate a 127 qubit chip, which is Eagle. As you can imagine, for each of those steps, we have significant technical improvements which are implemented in these different generations. And in 2022, we show a 433 qubit chip. And then it's really getting also very exciting, because we kind of break the 1,000 qubit barrier and reach more than 1,000 qubits in our Condor chip. And again, technological improvements are required for this. We are working on them. And this demonstration really is then a demonstration of above 1,000 qubits, and it will allow us, and also the world, of course, more complex problems to be solved. And this is integrated also with a whole infrastructure, right? Because it's not only about the hardware, there is also the infrastructure around the software, how to control, how to write software, developing applications, etc. So there are lots of things which are going on currently.
Wow, it's interesting that you just mentioned fundamental problems, and we've just actually received a question pretty much about that. So somebody here is asking, is quantum only for computing faster and having parallel processing, or is it also being used for answering fundamental physics questions?
That has different components, this question. And because quantum actually is, we call it fast. I mean, often it's called faster, that quantum computers are faster than classical computers, but that's not, we should phrase it differently because they actually use a different way of computation. And so for certain problems, they can be faster, but for other problems like your word processing, what you mentioned at the beginning, they may not be faster. So we cannot kind of generalize it. And but it also can be used, and quantum technologies are also used for sensing applications. So there is an advantage also for using the phenomena of quantum physics and quantum mechanics for other areas. And the third question was also, can we help fundamental basic experiments or whatever, right? And that's actually exciting because I mentioned before, many of the things are related to materials and improving materials. And so my colleagues have 35 years ago got the Nobel Prize for the high temperature superconducting, but high temperature was still only in the kind of nitrogen, liquid nitrogen region. And so the whole community is kind of looking also for high temperature, really high temperature, which means kind of room temperature superconductivity. And actually quantum computers may be able to help, right? And if we have the right system around, then the hope is also to predict materials which can solve those fundamental questions.
Wow. Okay. Well, and so just to go back to what you were saying about the qubits and how, like the superconducting qubits and how we're making them. So if I understand correctly, you know, quantum computers of the future will have like thousands of these physical qubits, that's physical things, right? That we're going to be cramming into this wonderful chandelier here, right? So I just can't imagine if we're cramming thousands and thousands of them in there, at some point, this whole beautiful thing is just going to collapse, right?
Yeah, so of course you know, this is kind of the start. It's not the end. It's there is I mean, this is also a small fridge, right? And for bringing like millions of qubits into such a fridge, it needs also different technology. And I said for each of these steps, we have new technology coming in. And one of the things which comes then beyond the 1,000 qubit is really kind of a so-called super fridge. So this is one technology which we are working on, this so-called golden eye. And we also have a picture here where you see it. It's you see the dimensions, right? I'm standing next to this one. So and Jay, who is our leader of the quantum program, he is actually inside this new fridge which we are developing, and this is also technology which we in-house develop in order to go to the next level, to really prepare everything and for being able to build also quantum computers with millions of quantum bits. So you see the fridge here is about 10 foot high and 6 foot wide. And it's already tested, and you know, certain feasibility tests are made, and there is further development towards having this ready when we then you know, get to these numbers. This is one example, but the other thing is if you continue scaling the number of qubits, then you also want to have technology available which actually connects different quantum processors. So we are working also on connecting different quantum processors. And so kind of create like an internet of where different quantum processors are connected with each other.
Okay, wow, great. Thank you for that. Another question from the audience here, kind of personal question. What use cases are you working on, Heike?
So I don't necessarily work on application use cases, but my team here, so Stefan Wörner and also Ivano Tavanelli and the team, with colleagues around the world at IBM, they're working on use cases, and also actually with a lot of partners in industry, because you know, we are the compute experts, and we work together with partners who are the industry experts to figure out what are the relevant use cases in each of the industries to go after and provide really the quantum advantage and the value for the industry. And so I hope, next time, Katia, for your next webinar, I already have a suggestion to invite Stefan and Ivana. They can tell you then more about their quantum applications they are working on.
Wonderful. Yeah, absolutely. Sounds fascinating. Another question here. If someone wants to work on quantum software development, what would you need to study? That's an interesting one.
Yes, though actually this is changing quite a lot, because we are developing a lot of the software stack. And today we actually have made an important announcement also to really make it easy, make it frictionless for people to develop quantum applications and use quantum computers. So we have for what do you need to study? I mean, today I would recommend take computer science, for example, right? But also have quantum courses. And I think that's actually where a lot of, but also physics and take computing courses. So I think it's right now actually a mix, because you should have a bit of a quantum physics background, but also have skills on the other side. And in the end today, we are really, you can use quantum computers already by just knowing Python and work with our the open source Qiskit work software to use quantum computers. So actually, it's a very easy level to go into programming quantum computers and work with quantum computers. And so these programs also in the education area there's a lot of dynamics, because in former time, as I mentioned before, only physicists kind of worked with quantum computers and programmed them, but this is really changing a lot. Today, these courses are already happening for all the different study subjects, whether it's from engineering, computer science, chemists, and etc., to kind of bring the basics for quantum computation.
Mm-hmm, mm-hmm. Yeah, well, and in my mind, now we kind of come, now that we mentioned education, we come to the most important topic of this discussion anyway. Heike, do you think the world is actually ready for quantum computing? I mean, okay, we've got these machines, right? But you mentioned that they're not. We haven't reached quantum advantage yet, so they're not better than classical computers just yet. But imagine if we do reach quantum advantage, say tomorrow, or like a week from now, or even 6 months from now. Do you think the world is ready for quantum computing? Like, will the companies around the world suddenly all be able to know how to use it, what to use it for, or not? What's your view on that? Are we ready for quantum computing?
Yes, I think people are getting ready, right? And I would say you better get ready, because it's really a very dynamic environment. A lot of things are happening. The technology is developing very fast, and different to classical computers, the scaling behavior of quantum computers is also different. So it's not like a linear scaling as we are used to in the normal transistor area, but it's really scaling with a different behavior. And so we expect that in 2023 actually, there is kind of a turning point where then we can demonstrate quantum advantage, and you are then better ready to can use quantum computers. So what does it mean using quantum computers, right? You should have identified like the areas where quantum computers can help you in your industry. What are the biggest pain points, the biggest challenges, where is the fit with quantum computers? And this requires, and also, of course, that you have a workforce which has a team which knows a bit about quantum and can have the industry expertise and can then also together kind of identify these workloads. And I think it's we are really in a dynamic world where you have to get ready because quantum computers are there and they will develop fast. And then there's an advantage and you are better able to use it.
Mm-hmm. I'm just getting more and more questions here, and the next one is actually we're gonna jump back to the beginning of the discussion. I'm sorry for that, Heike, but just rewind a little bit. This audience member is asking, can you please explain how quantum entanglement is used in how the quantum computer actually operates?
Yes, so entanglement is actually one of these behaviors which is also very weird because you kind of bring qubits together, you entangle them. This means they suddenly have properties which are really connected with each other. Then you separate them and you change one, you measure one, for example, and you exactly know also what the property of the other one is. And these are weird things which we are not used to in our daily lives in the classical world. But in the quantum world, they can be created. Qubits can be entangled. And they then also provide kind of the advantage or the power which is utilized by the quantum computation.
Mm-hmm. I remember reading that Albert Einstein once said that quantum entanglement was like spooky action at a distance. And it kind of makes sense, right? Because as you say, if one atom or qubit in this case changes its state, the entangled partner, even if it's like light years away, will simultaneously change its state too, which is like, I don't know, it's completely mind-blowing, right?
Yeah, because I mean, at that time, right, when it was clear that light travels at a constant speed, and light is needed to kind of transfer information, this was a real phenomenon. It was very hard to understand, and it's still kind of is, right, because it's not in our classical world present. So I think we also kind of get to have this intuition and for quantum mechanics and quantum behavior.
Yeah, absolutely. And so you were talking earlier about how people could use quantum computers even today, and I would assume in the future the process of actually connecting to a quantum computer would be similar, which is through the cloud. And we've got a question here from one of our audience. From one of our viewers who is asking how are quantum computers actually hosted or connected to the cloud, if you can explain the way they are connected to the cloud.
Okay, I mean, today we have a certain architecture. Perhaps we can also show the development roadmap in that regard, which also shows a bit holistically how we integrate the hardware, the software, and also then the building the applications. And we need to connect, of course, the quantum computer, which is sitting here, to classical computers. And through these classical computers in the cloud, you actually have the access. So that's why you can connect with your mobile phone or with your classical computer to the cloud and can access our quantum computers. But of course, there's a lot of things behind, which may go a bit too much into detail to explain here. But because you run certain circuits and you run algorithms, and we are continuously also developing that the architecture, which is actually has been announced today. So that's really brand new. This is an announcement of today, which you see, which is a holistic and integrated picture of the full stack development, which we do from the hardware to the software, and also the applications part, and providing then also the service through the cloud. And because we talked a bit about also what do you need to know in order to use quantum computers, and of course in the end we want to have like a frictionless development and frictionless use of people using quantum computers. This means if you are in chemistry and your job is to design new drugs, then you should kind of use the software and the tools which are used today, but behind the scene, quantum computers are used in order to solve the problems. But you should not need to learn kind of special things in order to use them in the most efficient way.
Yeah, I think you've just actually addressed the next question we have here, which is about exactly that. So somebody is asking, would one write custom quantum algorithms for applications now, or would algorithms mainly be written by academia or quantum experts and only used by the industry? So what's your view on that? I guess it's different now, and what you've just described was a roadmap, right?
Yeah, exactly. It's different now, but we are constantly developing and to make it much easier for everyone to use quantum computers and not be a specialist of, you have to kind of translate your problem into a quantum algorithm. And then it depends also on the hardware, how you implement it. And so you really need, we are developing this whole infrastructure that for the user, it's really frictionless to use them.
Mm-hmm. And so if we go back to what we were talking, like when we were talking about education and universities, so what is happening today? I mean, for people to actually understand what quantum computers can offer them in the future, do you think more universities should be kind of actively introducing quantum computing into their curricula, and maybe even on a high school level? And it doesn't, like, I don't know, in my view, it doesn't even necessarily have to be about programming specifically, but just to kind of introduce like 16, 17-year-olds to this idea that soon in the future, it will, like, if they will go into like material design, for example, they may have access to these machines that are just, coming online and will hopefully become fully functional in a few years from now. So do you think we should do kind of more in terms of educating the future workforce in that regard?
Yeah, of course. I mean, there is much more to do. It's also, of course, an exciting topic to learn about, and it will have quite some impact in the future. So as said, right, you're better prepared for it. And this means there are also different dimensions, of course. At the universities, for example, and in research, there is a really dramatic increase in also using quantum computers and working on algorithms. And so if you look around, whether it's in Europe or US and everywhere, the universities expand their programs in quantum computing, in the theory, and also using quantum computers. There are extracurricular made for, as I mentioned before, not that only physicists learn about quantum computers, but that also quantum computers, how to program them, how to use them, is taught to engineers and chemists and even finance experts, etc. So it's really broadening. This is what we see. We also develop actually quite a lot of tools and also programs where we help to bring together and to explain quantum computing, help people using quantum computers, show them how to program them. You can see, for example, YouTube videos where you can dive into detail in how to do it, and also in collaboration with universities. So that's the university level. Then if you go to the company level, it's again also, I mean, in the end, you want to also educate your workforce in quantum computing. You want to build up a team also of experts that they can identify the use cases and can also lay out a strategy for making use then of the quantum advantage and integrating it. In the high school, it's an interesting topic also, because I personally think the earlier you kind of get in touch with these weird phenomena, the easier it may be for you to grasp it and to think like it, right? Jacob Better also once said, you think too classically. And I think the earlier we start to see and visualize and experience quantum behavior, then the more an intuition we can, get. And having an intuition also helps to then actually become creative in that space. And so I think learning early, the way how to do it is, of course, different than how do you do it after you may have studied a certain subject. But I think there are cool things. I mean, for example, a colleague here, he looks into quantum games. So using the quantum physics and exploring how to use quantum computers in games. And that's also one way to kind of, get in touch with it and be excited about it and then learn about it.
Yeah, absolutely. I mean, quantum gaming, quantum video games, it's completely, I don't know, mind-blowing. I think when you're playing a video game and you know that it's been designed on a quantum computer, or maybe like you yourself could like design a quantum video game, I think it's absolutely amazing. So we've got another question here. Actually, we've talked about it a little bit, but Heike, could you just explain maybe a little bit more in detail for our viewers what is actually quantum advantage?
Yes. So quantum advantage we define as the state where we solve a problem which is of high value with quantum computers, which cannot be solved with any biggest supercomputer you can ever build in the world. And this is something where we expect this to come end of 2023, where we have reached kind of the 1,000 qubit barrier and have broken this barrier. And there should be then problems which really can be solved and provide the value with quantum computers. Today, as we discussed, these are smaller problems we can solve, but we learn a lot, right? Because we learn about how to write the quantum algorithms, which then can also be used with a scaled quantum computer.
Great. And so we talked about, creating more and more of these qubits, and hopefully, at some point there will be hundreds, thousands of these qubits, and we'll reach the point of the qubits being, quite good quality, right, so to speak. But do you think, there's a term in quantum computing, error correction. So what could you just explain? There's one of our viewers here is asking, what actually is error correction? What is it? Why is it important?
Yeah. So error correction is actually something which is used also in classical computers, right? In a memory cell, for example, when you store information, and you have ones and zeros, but sometimes an error happens, and then suddenly the zero switches into a one, and this brings you an error. So what you do is actually in classical, you kind of copy the things and have like 3 times the one. You store not only one, but you store it 3 times. And then if one switches, then you say, okay, that may be an error, and you can correct for it. And in quantum computing, that's unfortunately not so easy, because there is also quantum physics where you say you cannot copy a quantum state. So you need to find other tricks. But you also have like noise in the system, and you may also, when you do your calculations and apply your gates, you may the errors may appear, and so you also have to in the end correct for those errors to get the exact results. And this is important for the universal quantum computer. So we can also already do calculations like quantum simulations if qubits have still some errors. And this error correction needs then a number of qubits which work together in order to correct for this error which may appear. So the error corrected qubit has kind of more qubits than more qubits than a physical qubit.
Wow. So yes, it's fascinating that physicists are already working on this error correction, kind of looking into the future, right? And it's amazing. So once we get there, once we are able to create more and more of these physical qubits, we'll also hopefully be able to then apply these methods that we are working on today and correct those errors. So it's really work of the future, kind of shaping the future in my opinion. But what about the infrastructure though? So for instance, if we do reach quantum advantage, and hopefully we will reach quantum advantage, and then everybody starts, as you say, there's education and workforce development, and suddenly the whole world is using quantum computers. So how is it going to be? Can you just describe how many machines are we going to need? Are they going to be all tucked away in data centers, or what is it going to actually look like?
Yeah, so so just coming back to the error correction you mentioned, when we are above the 1,000 qubit barrier, then we can also start to do error correction, and then really the things getting a big momentum even more. And for the infrastructure, this means then you're able to you get the quantum advantage, and then there is also, of course, even more need for quantum computers, and we already see a lot of need for quantum computers. So we started in 2016 with 1 quantum computer online. Today, we already have 32 quantum computers online. And what does it mean? Today, they're actually in data centers. And as you know, a lot of data centers are used. There are many kind of mathematical problems I mentioned where you could use quantum computers. So I see this really expanding very much. And I mean, you know, someone said when the digital computers have been used or started in 1943, actually Watson said, oh, there will be not more than 5 computers in the world. And I think this, you know, we already passed. So it shows also a bit, I mean, looking back and you look at the semiconductor industry 70 years ago, would people have imagined that we, you know, use mobile phones for doing complex calculations, that you have mobile phones, that we do a video chat and all these things? So you see that actually having quantum computers, there will be more things which can be done with them, and there will be more development which actually expands into things which we may not be able to envision even today. And so I think it's really a very exciting time also to be part of this mission to create more complex quantum computers to reach the quantum advantage and to apply them in for very relevant problems.
Mm-hmm. Yeah, it's I mean, quantum data centers of the future. It just really sounds super cool. But what about AI, artificial intelligence? And there's somebody asking here, how can quantum computers help in deep learning? And indeed, I mean, we are making tremendous progress in AI, right? So I would assume that AI and quantum computers will have to work together somehow, right? What's your view?
Yeah, there actually also one application which I did not yet mention is machine learning, quantum computers and machine learning. And there's also a lot of research and development going on to develop new algorithms and also to figure out how can quantum computers help. And actually recently also quite important work has been done within IBM to demonstrate that the entanglement and quantum feature spaces can really help to improve the classification in data sets. And so we have also research projects where we, for example, work also together with the CERN here in Switzerland. As you know, they have very complex data sets. They have the Large Hadron Collider. They are preparing for new detectors to come where they get lots of data sets or lots of data. And they can actually not store all the data. So they have to extract patterns from the beginning. And so they just kind of then store the extraction, but this means they cannot go back and check later. And so with quantum computers, you could, because of the dimensionality, you can explore higher dimensional patterns or use the quantum computers and the entanglement to get to use quantum feature spaces where you can do a much better classification, thus provide also an advantage. So that is currently explored, and there are other similar examples also for machine learning.
Mm-hmm. Well, we have about 8 minutes left, so probably just enough time for 2-3 more questions. Heike, I know it's getting pretty late in Zurich, and everybody probably wants to go have dinner. But this one is pretty good. Could you tell us what are other interesting scientific technological developments that could influence the development of quantum computers?
So it's an interesting question. I mean, technologies which I've mentioned one, right? If you look at the fridge, because such a fridge is needed to really build to enable the millions of devices cooled. Then there are also other implementations of quantum computers, which you can think of where also more progress is needed. And then materials analysis in order to further improve the quality of the quantum bits, understanding where noise may come from, which is observed. And also quantum computers can perhaps in the end help by developing new materials, which then also provide new insights and improvements for the current technology. Mm-hmm. There's also electronics, which is developed. So the holistic system is really, improved and further developed in order to move to the bigger systems.
Mm-hmm. Well, I guess we only have time probably for the last question here, and it's an interesting one. It's on security. So what is quantum safe cryptography, and does it actually exist?
Can you repeat the question? Actually, I didn't hear it well.
What is quantum safe cryptography, and does it exist?
Oh, yeah. So quantum safe cryptography, I mean, people may ask, what is it, right? What does it mean? And quantum computers are so powerful, or will become so powerful in the future, that they may be able to actually factorize big numbers, which is for classical digital computers not possible. They may need like billions of years, but a quantum computer could, using Shor's algorithms, if you have a universal quantum computer, then do this like in hours. And this is still far away, but this is kind of a risk that then the current cryptography would no longer work. And therefore, we actually already also here at IBM develop quantum safe cryptography. And this is a different mathematical algorithm you use in order to encode your information. And this can actually not be solved very quickly by quantum computers. So it's a mathematical problem where quantum computers would not provide a speed up in order to then decode the information. Mm-hmm. And this is currently developed. I mean, there are quantum safe algorithms. There are like suggestions, and there is actually also competition of which ones will win and then will become a new standard for how to encode stored information. And as I mentioned, we have a team here who is working on this, and they already implement this also in storage parts that this can be sold and make your information already today safe for computers to come.
Wonderful. Well, thank you so much, Heike. That's really, really amazing and informative. One last question I have. When do you think we're going to have a replica of that to take home as a chandelier? Really?
I mean, we can use our skills, right? As you mentioned at the beginning, I have a furniture making background, so we can build our one.
Amazing. That's what I wanted to hear. All right. Well, thank you so much, Heike. Thank you so much, everybody, for joining us here today. If you have any other questions, just find us on Twitter, and we'll be happy to get in touch with you. And hopefully we'll see you at some point soon again. Thank you, and bye.
Thank you, Katia. Take care, everyone. Bye-bye.
Bye-bye.